Alright, so what I want to talk to you in this video is about a concept that some of you may have heard of before called buffers. Alright? Now, everybody, whether they know it or not, handles or deals with buffers all the time, and one of the most important buffers is actually your blood. Your blood's got to be able to buffer all sorts of funky things happening to it without getting messed up. In fact, the pH of blood can only work normally in a very, very, very small pH range. Usually it's between 7.36 and 7.42. And when you consider some of the crazy things that people put into their bodies on a daily basis, and I'm not talking about anything weird, I'm just talking about the kind of food that people eat, that sort of thing. When you have a particularly acidic diet, for example, that's going to eventually work its way into your blood, and there has to be a way for your blood to take in that extra H plus and not get all messed up, because if your blood is not within this pH, then you're going to have serious health problems. So a buffer is a solution that resists a change in its pH when either acid or base ions are added. Usually strong acid and strong base ions are added. The buffers, they work in a very, very simple way. They contain relatively large concentrations of a weak acid and its conjugate base. Now, when it says relatively large, that doesn't really mean anything. Relatively large concentrations relative to what you add. Alright? So you have a relatively large concentration of your weak acid, whatever it is, and the relatively large concentration of that conjugate base as compared to what you put in. So you're putting in a very, 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 very small amount of strong acid or base, and the buffer will kind of soak it up. So let's say, for example, you take a weak acid, for example, and its conjugate base, and you add in some strong base. What happens? Well, of course, that strong base would cause your pH to go up. Of course it would. You expect a pH jump, and that's exactly what would happen in water. Your pH would go from about 7 to 9, 10, 11, depending on how much OH minus you add in. If you add OH minus into a buffer, though, and this is very easy to demonstrate with a buffer, some water, and some strong base or strong acid, and some universal indicator solution. The fact is, when you add in that OH minus ions or H plus ions, and it's a very small amount that you add in, what happens is the pH of the buffer doesn't change. It doesn't change considerably anyway. So the OH minus, it does what it does best and looks for an acid, which in this case is the HA. So what happens is this reaction. That OH minus grabs that HA, forms water, and forms more of this conjugate base, right? So what this means is the concentration of your weak acid goes down, whilst the concentration of the conjugate base goes up, which of course means that these two change. But if the concentration of the weak acid and its conjugate base is extremely large, and the concentration of the H plus or OH minus that you're adding in this case OH minus, is really, 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 really small compared to this and this, then the fact is, although these two concentrations change, they change so little that the pH remains virtually the same. And the other thing is, of course, if the OH minus ions are used up, there's no way they can accumulate. They can't accumulate because as soon as another OH minus ion is added in, it gets eaten up by the HA. And there's so much excess of this that this really is like a, dropping a little pebble into the Arctic, I was about to say the Arctic Ocean, into, well, wherever, Atlantic, Pacific, whatever. It doesn't do anything. Okay, so we have a little bit of a pictorial representation here. So we have the original, let's say we have just made up a buffer, alright, and it's got a particular pH, whatever that may be, and on the next slide I'm actually going to show you about what's happening here and how to calculate buffer pH. So you add in some OH minus, and remember what we're saying is if we have OH minus that we add in, then the concentration of the HA that was originally in the buffer is enormous compared to the amount of OH minus that's added in. Now these are supposed to be greater than signs, not sound waves or anything stupid like that, so sorry about that. That means HA is much, much, much bigger than the OH minus. Okay? So when this happens, the concentration of your HA goes down because it gets used up by the OH minus. And the concentration of the A minus, because that's a product, goes up. But these change so little that because the pH of this solution is dependent on this concentration and this, in the final solution, after you've added in your OH minus and they've been replaced by these A minus ions, the pH is essentially the same because these concentrations have changed so very little. Okay? And that is the essence of how buffers work. The only way they'll work is if you have extremely large concentrations of your weak acid and your conjugate base, and you need large concentrations of both. Only one will not do. If you have a large concentration of both the weak acid and its conjugate base, and you add in a very small amount of either strong acid or strong base. If you add in too much strong acid or strong base, it'll just overwhelm the buffer. Okay, so it only works if you add in a very small amount of H plus or OH minus and you have large amounts of your weak acid and its conjugate base. Alright, so let's actually look at what's happening when you make up a buffer. What's happening is something called the common ion effect. Now some of you may have seen this before, some of you may have not. Let's say, for example, we look at a solution of 0.1 molar acetic acid. We've been through before about how to calculate the pH of a weak acid using an ice table and sticking an X and all that stuff. You've been through that before. And what that tells us is we have a pH of 2.9 for a 0.1 molar solution of acetic acid. 2.9 does not mean that's a strong acid. You have to be around 1 or 0 for that to be a strong acid. But what I want to show you here is what happens when we don't have just the acetic acid. I'm going to show you what happens to the pH and your system when you throw in some of the conjugate base of this guy. So here's a question for you. If this is our acid, HC2H3O2 acetic acid, what is the conjugate base of that? Well, of course, it's just the whole thing without the hydrogen there. Because that hydrogen is H+, then that means that this guy is, that's the conjugate base. Alright, I'm going to draw up an ice table here. I'm going to show you something. If I have an equilibrium set up between the acid and my water, which I always will, and I add in some of this acetate, in this case let's say it's sodium acetate that we add in. Remember Le Chatelier's principle and what that said? If I add in some extra acetate, which way is the equilibrium going to shift? Or which way is the reaction going to shift to re-establish the equilibrium? Well, of course, it's going to shift away from the side where you've added in extra material, which is this side, so it's going to shift to the left. Now, what that means, and this is important to understand, when the reaction shifts to the left, what has happened to the amount of your H3O+? Because remember, that's where the pH comes from. Well, the amount of your H3O+ has gone down because you've shifted away from it. So what that means is, whenever you take a weak acid and add in a salt of its conjugate base, the reaction shifts away from what you added in, causing more of the undissociated acid and making it less acidic. That's the common ion effect. You add in the common ion, the reaction shifts away from it, and when you have an acid, makes it less acidic. So what that means is a buffer of a particular weak acid is always going to have a higher pH. It's always going to be less acidic. Let me show you what I mean by that. We're going to fill up our ice table in the same way that we would normally, except our numbers are going to be a little bit different. We know that our initial concentration of our acetic acid is 0.1 molar. We also know that our H2O is not going to be involved. We also know that initially our H3O+ concentration is 0 because the reaction has not started yet. And if you remember previously, we did the same thing for our acetate. We assumed that was 0 as well, again because the reaction hadn't started. But here's the difference. We have just said I'm going to add in some acetate, and in fact I'm going to add in enough acetate to give it also a 0.1 molar concentration. So notice the difference now. It's not 0.100, it's 0.1.10. I didn't add in any H3O plus, I added in some acetate. We have no equilibrium concentrations, but we can do our changes again. We can just say that's represented by X, and X, and X. Now here we've got to be careful again about the signs of our X. Before we had both 0, so it was very clear which side was going to increase. So it doesn't take, well, let's see what you guys think. Which side's going to be plus and which is going to be minus? Well, of course, this side's still got to be plus because you still have a 0 there. That can't decrease. So plus X, and of course that's minus X. So what that means then is our equilibrium concentrations are going to look like this. So we've got that, we've got this, and then we've got this. Okay. Now let's write out our equilibrium expression, because I'm sure you will remember how to do that. For acetic acid, the equilibrium expression is products over reactants, if you remember. So the acetate concentration times the H3O plus concentration, all divided by the undissociated acid concentration. Now, remember we said before this is a weak acid. We're going to make our assumption. Oops. Dude, what happened? Oh man. Okay, where did that go? Where did that go? Alright guys, sorry, I don't know what happened there. Sometimes when I have my email open, and a new email pops in, the email box just pops up and removes everything else. Could you have anything naughty there? Alright, okay, so here's our equation again for the equilibrium expression. Alright. Now, because acetic acid is a weak acid, again, we're going to make that assumption. We can check again afterwards just to be sure. But let's just make that assumption that because it's a weak acid, X is very small compared to the initial concentrations here. So what that means is, and this is where things are different, not only is X small compared to this, X is also small compared to this. Alright? Now, when we do that then, we can say that the concentration of our acetate is 0.1, the concentration of our H3O plus is X, the concentration of our undissociated acid is 0.1. Our Ka, the Ka for acetic acid is actually 1.8 times 10 to the minus 5. Alright? And notice what this means is the two numbers here are actually the same, top and bottom. And so when you solve for all that, you can just get rid of those two. And so what that means is X is equal to 1.8 times 10 to the minus 5. So therefore, my H3O plus concentration is 1.8 times 10 to the 5 molar. Not there, is this. Alright? Let me just erase that. Okay, so that's my equilibrium concentration of H3O plus, and of course that's what I need to determine my pH. So pH, of course, is the negative log of my H3O plus concentration, which in this case is 1.8 times 10 to the negative 5, which in this case gives us 4.74. You remember what I said before? The pH of a buffer is always going to be higher than the pH of the acid that made it. And that's exactly what we see here. Now let's just check our assumption is valid. Alright, that's our initial concentration. Here is our Ka. Sorry, here's our X. We want to make sure this divided by this multiplied by 100 to get the percentage is less than 5%. I can already tell it's going to be way less than 5%, but we'll just do it anyway. Divided by 0.1, again times 100 because this is a percentage, and what this ends up being is 0.018%. So we are way within our boundaries of the assumption being valid. Okay, so we have calculated the pH of a buffer. Alright, now it turns out, because these two numbers here were exactly the same, that has ramifications for calculating pH later on, because there is actually a much easier way to calculate the pH of a buffer, and I'll show you that in a later video. But the important thing I wanted you to see is that the pH of a buffer is always higher or less acidic than the acid that it was made from. Alright, that's the common ion effect. We've talked a little bit about how buffers work, and that is it for now. Thank you, and sorry about the balls up partway through.